Hello, my name is Dr. Mark Walters. I'm the director of the University of California, San Francisco Alpha Stem Cell Clinic, and I'm pleased to participate in this session that will focus on a disorder or a group of disorders that I've had a lifelong interest in, which are hereditary blood disorders. And specifically, we're going to be talking about a disorder called thalassemia, which is a hereditary disorder. It is diagnosed shortly after birth and is caused by a defect such that not enough hemoglobin is made. So hemoglobin is the very important protein in the blood that carries oxygen to all our tissues and is absolutely necessary for life. So a baby who's born with thalassemia, there are a couple of different types that we'll talk about, is not able to maintain a healthy hemoglobin level. And so red blood cell transfusions are generally started in the first few months, first few years of life, and then are needed lifelong in order to sustain life. And the challenge is that this is a cumbersome treatment coming in once a month for a transfusion. It leads to complications. A common one is excess iron that develops in the body that can poison the heart and other organs in the body. And the first patient we treated in Oakland is shown in this picture. So this is a picture of a child and her mother who had a form of thalassemia called alpha thalassemia major. And a little background information about this form of thalassemia, it almost always results in the fetus dying of anemia before the baby's born. But rarely, very rarely, a child will survive to birth, at which time transfusions can be started and the child can be rescued from the alpha thalassemia. So as it turns out, this little girl, who was 3 years old at the time, had a transplant type matched donor, a sister who had what we call the same HLA type as she had, and we performed a bone marrow transplant, and she was cured of the alpha thalassemia major. So that was terrific. So if we could move fast forward 15 years later, I'm working with a colleague at UCSF, a pediatric surgeon, Tippy McKenzie, who has developed a protocol to explore an idea that that builds on the observation that you could start these transfusions before the fetus is born and actually get them safely to birth. And in fact, if you give this same fetus a small infusion, a small dose of the mother's blood stem cells, you might then also begin to cure the alpha thalassemia. The first step is to make that fetus, who has a very undeveloped young immune system, tolerant to her mother's blood stem cells. And then after the baby's born, we can top off that same baby with more of the mother's stem cells and get enough of them to take to be able to stop the red blood cell transfusions. So the advantage of this approach, if it's successful, and this is very exciting, is that one, you can get many more of these babies with alpha thalassemia to birth safely. And second, shortly after the born, you can institute a curative therapy that would help them stop the transfusions and live a healthy life. So that's how that started, and that's how we are today. And much of that is really a credit to California Institute of Regenerative Medicine and the very important funding, the extraordinary funding opportunity they've given Dr. McKenzie to be able to carry out this very important protocol. Now I'm going to shift to the next part of the story, which is a tribute to my colleague who passed away recently, Bert Lubin, who was a member of the Independent Community Oversight Committee for a number of years for CERN. And Bert had this idea that if a child has thalassemia, let's say, and the family, a young family, is expecting a new baby, a full sibling, we should have a national public resource to collect the cord blood, which is the blood left over after the birth of the baby, so that we can use that resource to perform a transplant for the child affected by thalassemia, the older child. And this next picture shows two examples. On the right, a little girl who was the donor whose cord blood was given to her older brother for thalassemia, and he was cured of thalassemia after the transplant. And then the smaller inset on the left is a picture of two sisters, the older of which had sickle cell disease, another hereditary blood disorder that was cured by a transplant using that leftover umbilical cord blood. But still, we had a problem, which is that very few children with thalassemia or sickle cell disease, for that matter, have a fully matched donor, a brother or sister who, by chance, they've inherited the same transplant type. So again, we're going to go fast forward 15 years later, and this is the topic that you're going to hear more about, which is gene therapy for thalassemia. So in this protocol that's now maturing, we can actually harvest blood stem cells from a person with thalassemia and then at a manufacturing site inject those blood stem cells with a healthy copy of the globin gene so that they can make hemoglobin that those stem cells couldn't make. We then reinfuse the modified stem cells, and when it works, it's spectacular because the hemoglobin promptly comes up on its own. The transfusions that were previously needed to sustain life can be stopped, and we can actually eliminate the excess iron quite quickly after the transfusions also are stopped. We're quite optimistic about the future, which is that I think we're at the cusp, either using this technique or others very much like it, where we can modify the blood stem cells in a person who inherits a hereditary blood disease, give those stem cells that have been modified back, and then alleviate, if not cure, the underlying disease.